Welcome back. In this lecture we're going to be looking at the SYCL system topology and how to create a queue so you can start submitting work to a device. In this lecture we're going to cover the SYCL system topology and how to traverse it, how to query information about a platform or a device within the topology, how to select a device both manually and using device selectors, how to configure a queue, and then finally the SYCL scheduler and how to submit work. First of all, let's take a look at the SYCL system topology and how it's structured. A SYCL application can execute work across a range of different heterogeneous devices, and the devices that are available in any given system are determined at runtime when you do topology discovery. When querying the topology of a SYCL system, there will be a number of platforms available. Each platform is an implementation of a particular backend. For example, an OpenCL backend for Intel and an OpenCL backend for NVIDIA are different platforms. This is an important distinction because platforms can generally not communicate directly with each other, and we'll see this come up in a later lecture when we cover data movement. Each platform will also have a number of devices associated with it. These can be CPUs, GPUs, FPGAs, or any other kind of accelerator. In SYCL there is also a host device, which executes SYCL kernel functions natively within the SYCL runtime. The host device emulates the execution model and memory model of a regular SYCL device. This can be very useful for debugging SYCL applications, as some devices may not have native debugging tools available. There is always one host device. Each SYCL implementation must have one, and there can only be one. The host device is also associated with the host platform, and again there can only ever be one host platform. Platforms and devices are represented by the platform and device classes respectively. A default constructed platform object creates a host platform, and a default constructed device object creates a host device. Now there are two ways in SYCL to traverse the topology of a system. Firstly, there are APIs which allow you to manually query the available platforms and devices. Secondly, there is a mechanism called device selectors for automatically traversing the system and producing a device based on a heuristic for scoring devices. First, we're going to take a look at how you would manually traverse the topology of a system. The platform class provides a static member function called getPlatforms. This returns a vector of all the platforms available in the system, including the host platform. So in this example, where we have two OpenCL platforms and a host platform, getPlatforms would return all three of these. The platform class also provides a member function called getDevices. This returns a vector of all the devices associated with a specific platform, including the host device. So in this example, where the Intel OpenCL platform has a CPU device and a GPU device, if you were to call getDevices on the Intel OpenCL platform, it would return both of these devices. Alternatively, the device class also provides a static member function called getDevices. This returns a vector of all the devices available in the system for all platforms. Again, this includes the host device. So in this example, where we have 4 devices across our 3 platforms, getDevices would return all 4 of these. Next, we're going to look at how to traverse the topology using device selectors. To simplify the process of traversing the topology and selecting a device, SYCL provides the device selector mechanism. A device selector is a function object which inherits from the device selector class. A device selector provides a heuristic for scoring devices. SYCL provides a number of standard device selectors, but users can also create their own custom ones. The device selector class provides the member function selectDevice, which will traverse the topology for every available device, pass each of them through the device selector, obtaining a score for each, and then it will choose the device with the highest score. Any device with a negative score will never be chosen. Here we have an example of constructing a device selector and calling the selectDevice function to retrieve the resulting device object. The default selector is one of the standard device selector types provided by SYCL. The default selector will choose a device based on an implementation-defined heuristic, so the device that is chosen by this can vary from one implementation to another. Okay, so now that we know what a device selector is, how do we create one of our own? So it's actually pretty straightforward. A device selector must inherit from the device selector class, and a device selector must provide a function call operator which takes a reference to a device object and returns an integer. The body of that function call operator is the logic which defines the heuristic of your device selector. This is how you define how each device is scored, and the value returned is the score for the device that is passed in. In this example, we return a positive score for each GPU device and a negative score for everything else. However, this logic could be much more complex, querying the vendor or the capabilities of the device. If you end up with more than one device with the same score, then the one that is chosen is implementation defined. Now that we have our device selector, to use it we can simply pass it to the constructor of the queue, and this will create a queue which will enqueue with the resulting device. There are a number of other ways to configure a queue, and we'll touch on some of these later in this lecture, but this is the most common. Now we've covered how to create a device selector, but how do you decide what to score each device? So in the body of your device selector's function call operator, you can query the device or its platform for information about it to determine its score, depending on the heuristic that you want to define. You can do this by calling the getInfo member function template, providing one of the many enum values corresponding to different pieces of information that you can query. You can retrieve the platform associated with any device by calling the getPlatformMember function. Here we show some of the information that you can query, but for a full list of these queries you should see the SYCL 1.2.1 specification or reference cards. So now we're going to take a look at what a queue is and what it does. But first, before going into what a queue is, it's first important to understand what a context is. A context in SYCL is an object which manages the underlying resources of a platform and a number of devices. A context can represent one or more devices, but they must all be associated with the same platform. So in this example, we've created a context for the Intel OpenCL platform and both its devices. Now a queue in SYCL is the object which is used to submit work. There are many ways to configure a queue in a SYCL application, from the very simple to the more complex, but every application must have one. A queue's job is to process command groups and submit commands to the scheduler for a particular context and device. A SYCL application will often want to target multiple devices. This can be useful for task-level parallelism and load balancing. Here we have two queues, one for the CPU and one for the GPU, both associated with the same context. This is important for being able to communicate efficiently between the two devices. So how do you create a queue? There are a number of ways to do this, some involving more complex configurations of contexts, but in this lecture we're just going to focus on the most common. The simplest way is to default construct a queue, which will use the default selector. This will create a queue which is associated with the device that is selected by the default selector and will implicitly create a context for it and all other devices associated with the same platform. So in this example, if we assume that the default selector chooses the Intel GPU device, then we will create a queue for the Intel OpenCL GPU which has an implicit context which is associated with that device and the Intel OpenCL CPU as well. Next, as we've seen in earlier examples, you can construct a queue from a device selector. This will create a queue which is associated with a device that is chosen by that device selector and implicitly create a context, just as before. So in this example, we end up with the same result, but here we explicitly request an Intel GPU. So now that we have a queue, how do we submit work to it? In SYCL, all work is submitted to a queue. This is done by using the submit member function. This will process a command group and submit commands to the SYCL scheduler for the context and device associated with that queue. So here we submit a command group to the GPU queue where it is then processed and submitted to the scheduler. Then once the scheduler decides to execute those commands, they are then enqueued to the target device. The same scheduler is used for all queues in order to share dependency information and maintain a single ordering of commands. So in this case, where we have two command groups submitted to different queues, each queue will process their respective command groups and submit them to the scheduler. The scheduler will then decide the ordering of the commands in each command group based on the dependencies of each, and then enqueue the commands to the target devices in that order. The submit member function takes a callable, which can be either a function object or a lambda expression. The callable must take as its parameter a reference to a handler object. The handler is created by the SYCL runtime and passed into the callable by the submit member function, so you cannot manually create a handler. The body of the callable represents the command group scope. This is where you construct a command group. And you do this by associating dependencies and commands with the handler object, but we'll cover this in more detail in later lectures. The command group scope is called exactly once, and when this function returns, the submit member function will then construct a command group. This command group is then processed and submitted to the scheduler, where its commands are enqueued asynchronously. A queue object will not automatically wait for submitted work to complete when it's destroyed. There are other ways to wait for work to complete if you have data dependencies, and we will cover this in a later lecture, but it can also be useful to explicitly wait on the queue to complete any outstanding work. You can do this by calling the queue's wait member function.